In this project, we see that there is a fire hose reel in network section 2.19. The fire hose reel requires a discharge pressure significantly higher than that of the sprinklers. Therefore, from this point, we know that the pressure at point 3 will be quite high and will result in a discharge pressure at the sprinklers higher than desired. For this reason, the pressure at point 3 must be regulated using a pressure-reducing valve. First of all, we need to perform the calculations to observe the initial results of this specific group, without applying any pressure regulation. Initially, in network section 2.3, we can see the components and notice that there is no pressure reducer installed. By selecting the group results, we can observe the calculations carried out for this group. What we initially see is that the discharge pressure at the fire hose reel is 4.94 bar and the discharge pressure at the most unfavorable sprinkler is 2.08 bar, while the required pressure is only 0.7 bar. This results in a sprinkler flow rate greater than desired, which in turn increases friction losses, flow rates of all sprinklers, operating pressure, and in some cases, may even require larger pipe diameters. Therefore, what must be done is to bring the discharge pressure at the most unfavorable sprinkler as close as possible to the required discharge pressure. We return to the CAD environment. By following the path AutoNet, fittings and opening the drop-down menu, the pressure-reducing valve PRV, as well as the bypass valve PBV can be found. At first, we pick the part of the network where it will be placed, in this case the pipe shown. After choosing its position, we input the required pressure. Initially, we test the PBV, and we input 1 bar. After completing the network recognition, opening the calculations sheet and updating from the drawing, we open the group results. Returning to the group results, we observe that the discharge pressure has decreased as expected, but it has not yet reached the required level, since the friction losses have also decreased accordingly. Therefore, we return once again to the CAD program in order to increase the pressure drop and carry out a few more iterations, until we achieve the desired results. We will assign a different value to the valve. This can be done by going back to the CAD environment, clicking on the and scrolling down on the Properties tab. From there, we can assign a new value. Once again, we use the same procedure to move to the calculation sheet. We repeat this process, until the desired value is found. With a pressure drop of 2.6 bar, we observe that we are getting very close to the desired outcome. We see that the sprinkler flow rate, which was 82 liters per minute in the initial calculation, has now been reduced to 48.3 liters per minute. In conclusion, we need to apply a pressure drop that brings us as close as possible to the required discharge pressure at the most unfavorable branches. In our example, this was achieved with a pressure drop of 2.6 bar. At this point, we will see what happens if we apply a greater value than necessary to the valve. We can change the PBV and PRV values from the calculations sheet too, as shown. We see that while the discharge value is the same as the required one, the pressure in the network section before the reducer has increased significantly, leading to a much higher discharge pressure at the fire hose reel, which will again provide incorrect results. Another method to regulate the system is to set the desired pressure directly at point 3. An initial calculation we can make is to add up the friction losses and the required discharge pressure and assign this value to section 3. The PRV is added to the network in the same way as the PBV, with a drop value of 2.46 bar, as initially calculated. As in the previous procedure, we expect a decrease in friction losses following this approach, and therefore a reduction in the required pressure at point 3. We will again perform iterative steps until we achieve the desired result. If we assign an operating pressure that cannot cover both the friction losses and the sprinkler's discharge pressure, then the group results will appear blank. Once again, through iterative procedures, we managed to determine the optimal operating pressure for this specific point. In this way, we achieved the best sizing of our system.